Today, I'm pleased to introduce today's session, Vector Database 101, a crash course, and our guest speaker, Yujin Tang. Yujin is a developer advocate here at Zillis. He has a background in software engineering, working on auto ML at Amazon. Yujin studied computer science, statistics, neuroscience, and has research papers published at conferences, including IEEE Big Data. He enjoys drinking bubble tea. I can confirm this. Spending time with his family and being near water. Welcome, Yujin.
Oh, thank you, Emily. Hello, everybody. So today we're going to be covering Vector Database 101. And the basics of what we're going to cover today is we're going to start with kind of an overview of how, of the problem that vector databases solve and how they let you work with unstructured data. And then we're going to dive into some use cases, how they work, and then we're going to go through a demo at the end. So first, a little bit about me. As Emily mentioned, I'm a developer advocate here at Zillis, and I love bubble tea. And in the QR code there, or in the screen, on the screen there, to your right, there's a QR code that will take you to my LinkedIn if you would like to connect and ask me questions later. A little bit about Zillis before we get started. So Zillis, we were founded in 2017. We're based in Redwood Shores, California. And we are the maintainers of a bunch of open source projects. And the ones that are most relevant to what we're talking about today are Milvus, which is our open source vector database, and GPT Cache, which is our open source semantic cache. Okay, so today we're going to cover these topics in this order. So we're going to do Vector Databases 101 kind of like review, an overview of the data, of the types of data that you get to work with and some of the use cases, and then how vector databases work, and then a demo. Okay, so Vector Databases 101. Why vector databases? What's the point? So I think the first kind of thing to talk about here is that vector databases are meant to work with unstructured data, and unstructured data is 80% of the data in the world. And vector databases is the only type of database that do this. And the way that these are different from, let's say, any other database, like a SQL database or a NoSQL database, is essentially the search pattern, the search types, right? So in SQL databases, in NoSQL databases, you're doing a lot of key-to-key matching. You're trying to find, like, hey, I'm looking to select XYZ, where XYZ from, something like that, right? So you're doing a lot of key-to-key matching. And in vector databases, what you're actually going to be doing is a lot of vector comparisons. And vectors are these representations of unstructured data that are really just long series of numbers. And so vector databases are specifically built to work with this type of unstructured data, including text, images, videos, audio, by turning it into numbers and then allowing you to quantitatively work on that. So let's kind of just cover some examples of why text or why different kinds of unstructured data might be hard to work with. So first, we're going to look at something around text, and then we'll look at something around images. And so this is going to be an interactive portion of the presentation. So get ready to type into your chat, okay? So here, when we're looking at text, we're doing some sort of keyword search. One thing that you might miss with regular keyword search that you might be able to pull with vector search would be something like the semantic meaning and the context and the user intention, right? So for example, here you have an apple, and you could mean an apple like the fruit, or you could mean apple like the company. And then there's something about rising dough and proofing bread. And then there's car tires, right? So if you want to change your car tire, are you looking to get instructions on how to actually change the car tire? Or are you looking to know when you should be changing your car tire, right? So with text, there's a lot of meaning and context and things outside of just the text itself. And so doing this keyword search is not always going to be good enough. A, you may not get the right results back, but B, you might not even get the right intention back, right? So then this part is the interactive part of the presentation. So here I've got some pictures of a very, very famous celebrity, my favorite celebrity, Taylor Swift. And what I would like to know from you guys is, which one of these pictures do you think is not Taylor Swift. So I'm gonna take a pause here, and I'd love for you guys to put some number into the chat, either 1 for this one right here with the very red one, 2 for the second one here, 3 for the one that's, she's got like the black top on, and then 4 for this last one where she's wearing this little sparkly dress. Let's see, 2, 4, 2, 3. This emoji, that's not really a number. Okay, looks like there's a lot of guesses out here, a lot of disagreement. I'm gonna let some of these answers trickle in before I tell you guys. So hopefully this exercise here gives you an idea of what it's like to perform the operation that a vector database might perform. In this case, the operation here is similarity search for images. And those of you who said 2, by the way, you guys are correct. 2 is the one that's not actually Taylor Swift. All of the other ones are Taylor Swift. I see there's a lot of 3s and even a 4 out there, but I guess everybody knows that this one here is Taylor Swift. This must be a very iconic picture. Okay, so these vectors that are numbers, how do they work? Where do we get them? Let's start with our knowledge base, which in the examples before would have been some sort of text, would have been the pictures of Taylor Swift. In an enterprise setting, probably for work, for you, it's probably your actual internal documents. So what happens with this data is it gets passed into a deep learning model. And it's really important here that the deep learning model that you have is the right type of model. It's got to be trained on the right type of data. If you're working with images, you got to have a model that's been trained on image data. If you're working on text, it's got to be trained on text data. If you're working on images and you're specifically looking to identify types of cats, you got to have that in the data, right? And so what happens is you take your image data and you run it through a deep learning model, and then you cut off the last layer. So the last layer of a deep learning model typically does the prediction, right? So let's say, for example, you have an image model. It'll typically do some prediction like, yes, there's a cat in this picture, or no, there's not a cat in this picture. But what we want is we actually want to know what the model has learned about that data, and we don't want it to give us a prediction. We want to just know what it's learned, so we have the numerical representation so that later on when we want to work with that data, we have a way to quantitatively work with that data. So the way we do that is we cut off the last layer and we take the output from the second to last layer. So why the second to last layer and not any of the other layers in the middle? It's because as you pass data through a model, each layer will learn something new about the model, and the second to last layer contains all of the semantic information without doing the prediction. And that is basically what a vector is. And then you take that vector and you put it into a vector database like Zillis or Mildus, and later on you can query and compare other information to that vector. So it's important to also understand that the information that you compare has to all be the same length, the same dimension of vectors. And we'll cover that. We'll take another look into that at a later slide. Okay, so how do you use vector databases, right? How do you actually use these? So here are 9 use cases for vector databases. The most popular one that we've seen over the last few months, over the last year, basically, has been RAG, retrieval augmented generation, right? It's right here. It's in the top corner. If you've heard of RAG, drop something in the chat. Let me know what you've heard about it, or if there's any questions you have about RAG, drop that in the chat. And outside of RAG, there's a bunch of other things as well. So there's recommender systems. So for example, product recommendations is actually one of the most common use cases and one of the most common use cases in production for Mildus, right? Products are complicated things that have text and images and reviews and all of these different things attached to them. And so recommender systems, what they'll do is they'll be able to compare these products and these users and use a vector database to quantify that and compare that. Other examples, right? The text search, we just talked about that. The image search, we're going to talk about, we just talked about that. Video similarity search, if you can do video to video search, that'd be great. Audio similarity search, anomaly detection is another really common one. How different are two user actions? Is it really the same user? And this is super important when it comes to things like fraud detection, right? And then the last one that we have listed on here is multimodal search. And this is something that we're going to be working on more in 2024. We're going to be creating some tutorials on how to do multimodal search. So let's look at some examples. So in this example here, in this slide here, there is a QR code to the right, and there's a bunch of pictures right here. right? So these pictures are all paintings, and I believe they're all of the ones here are impressionist paintings, and these are all the search pictures. So what this notebook walks you through is essentially how do you ingest these pictures and compare other pictures to them. So pictures do take a while, so this notebook will take you somewhere between 12 to 15 minutes to run, but so check it out later. And then another example that we have here is text search, right? So we just looked at image search, and now we're going to take a look at text search. And later on for our demo that we're going to walk through, we're going to be doing something with text as well. And so in this text search, what we did was we just scraped Wikipedia. Basically, I scraped a page from Wikipedia, The Nightmare Before Christmas, and I asked, what is the plot? And it says, the plot of The Nightmare Before Christmas revolves around Jack Skellington, the Pumpkin King of Halloween Town, who becomes tired of the same routine of Halloween and discovers Christmas Town. And then it goes on and it tells you about the rest of the plot of The Nightmare Before Christmas. Okay, so how do vector databases actually work? What's going on beneath the surface? So first, let's look at an example entry. So this is what you might store in one entry in a vector database. The two most important pieces of this entry are the ID and the embedding. So the ID is your the way that the vector database is able to have a unique ID on your entry, and then the embedding is the actual vector embedding. This is what gets compared when we go and we search through and compare vectors, right? So this is why earlier I was saying, vector databases are a specific type of database that are optimized for a specific type of use case, and that use case is to compare embeddings and to do this kind of high compute task. And then in addition to those two fields, we also have a bunch of metadata fields in this example, and these are fields that you can filter on basically. And for this example here, what this is actually, this is an example from a demo app that I made for chat towards data science. And actually this uses Zillow's Cloud. Okay, so let's look at the one of perhaps the core functionality behind the vector database. This is like the very basic functionality. This is semantic similarity. This is what the vector database does for you. So in this example, we have 4 words that are all set up as 2-dimensional vectors. And before we get into the example, I want to be clear that this is a toy example, that you will never see companies using 2-dimensional vectors for words. That'll be really weird. And then I also want to point out here that queen and woman and king and man have the same value on the first axis or the first dimension. And all that means here is that these words have the same value on that dimension. It doesn't tell us anything about what that dimension means. It just says that these words relate the same way along that dimension. So it could be, for example, that 0.3 correlates to words with 5 letters, and 0.5 maps to words with either 3 or 4 letters, right? So I just want to point out this dimension doesn't necessarily respond to, or correspond to a discrete concept in our world, I guess. So let's take a look at the math behind this, right? So queen minus woman plus man equals king is the idea behind this slide. So queen is 0.3 comma 0.9, and woman is 0.3 comma 0.4. And so the difference there, if when you subtract them, by the way, this is called Manhattan distance when you just do the subtraction. This is also usually not implemented. And this example is 0.5. And then we're adding man, which is 0.5 comma 0.2. And we'll see that adding that together gives us 0.5 comma 0.7, which maps directly to king. So the example, the idea behind this example is that you can do math on things that are not originally numbers using vectors. And in the example, we used words. Okay, so let's look at some of the actual similarity metrics, right? So I said the way that we're doing the math in this slide, I called this Manhattan distance, right? So let's look at distance metrics that we actually do use in vector similarity search. So Manhattan distance is just, QI minus PI, basically. So this is Euclidean distance. And this is probably very familiar to most of you. If you've taken anything beyond algebra 2 or geometry, whatever, you probably have an idea of this line, I guess, this concept called a hypotenuse in right triangles. And essentially that's what the L2 or Euclidean distance is measuring. It's x squared minus y, or x1 minus y1 squared plus x1 minus x2 squared plus y1 minus y2 squared. And in practice, in Milvis, we actually don't do the square root because that's just extra calculations, and all the distances actually come out to the same rank order, sorry. Okay, so the next one is IP. And so earlier we just saw Euclidean. This measures distance in space, right? This is basically, if you have a right triangle, measures direct distance in space. IP is a little more complicated than that. What this measures is this measures the distance, this measures the projection of one line onto another. So if you were to imagine here, instead of saying that, oh, these 2 points, we're going to do the hypotenuse, what we're actually going to do is we're going to say, like, we're projecting from the origin these 2 points, and this the IP is the projection of this point onto another. So it's like, how do you project that at a right angle? And this essentially measures not just the angle difference between two vectors, but also the space distance between two vectors. So this measures difference in orientation and magnitude, and L2 is just magnitude. Now the next one is cosine, which just measures orientation, right? So we have magnitude, orientation, and magnitude. So cosine, the way that you think about this, is basically just the difference in angle between two vectors. So vectors can be thought of as both points and lines that point to points. And so basically with cosine IP, you're thinking about them as the lines that point to points. And with cosine, you're just thinking about how big is that angle between my two vectors. And so one thing you'll notice here that's kind of interesting is also that cosine and IP look very similar. So you see IP is sum of AI, BI. Cosine has that up in the top numerator. And so cosine is actually just normalized IP. And so if your vectors are all normalized, which means if the magnitude of your vectors is all 1, then you should just be doing IP and you get the exact same value as cosine. So when it comes to picking which of these metrics to use, you need to be thinking about basically, do I need to measure like how far apart these concepts are, or how far apart maybe the meaning behind some of these concepts are, and are my vectors normalized and things like that. Now, it's important also to note that, these all have the same rank order. So no matter which one you use, the rank of the vectors that you get back should pretty much be the same for all of them. Or it should be the same for all of them. So now let's look at some of the ways that you can access indexes. Indexes are the way that you store your the way that you reach your data. So the way that you find your data, the way that you search your data is determined by the index. So what we just talked about was the distance metric, which measures how far, which tells us how we measure how far our data is from each other. And then this tells us how we look for points in our data. So inverted file index, or IVF, is probably the most intuitive vector search method. And the way that you can think about this is basically just, I'm doing a bunch of k-means. I say there's going to be some number of centroids, and then we just cluster and we find all of the vectors that are closest to those centroids, and we create these clusters. And then what happens at search time is, first we search the centroids for the closest centroids, and then inside of each centroid we search the actual points. And we can actually do that, either search all the points or through a quantized version, which I'll talk about in a further slide. The next index that is of importance is HNSW, or Hierarchical Navigable Small Worlds. And this is a graph index. And essentially what this does is it takes all of the points in your vector space and it inserts it into a graph. And as it's inserting it into a graph, it assigns a uniform random variable. And depending on the value of that variable, you're going to be assigned a layer. So all points go into layer 0. And then if your variable is within a certain range, if your uniform random variables within a certain range, you go to layer 1. And then once again, if your variables within a certain range again, you go to layer 2. Now it's important to note that all points in layer 1 are in layer 0, and all points in layer 2 are in layer 1. And what happens at search time, you start at the topmost layer and you go and you find the closest one, and you drop down, you find the closest one, you drop down again and again and again. So HNSW is very accurate because it saves all of the distances in the graph, and it's very fast because all distances are saved. The trade-off here is that HNSW takes up a lot of space. As you can imagine, you have to store things multiple times. Okay, the next part of the indexing thing that you want to know about is quantization. So this is what we call scalar quantization, which is quantization along one dimension. And quantization is pretty much, I just think of this as bucketing, right? So if we have the list of reals, now we have the list of integers. So maybe you have -3 to 3 as real numbers. And now you say all the values from -3 to -2.5 are -3. And all the values from -2.5 to -1.5 are -2. So it's just bucketing. And what this does is this allows you to save and store a lot less information on disk, but you get a lot less granular of a search. And then next is product quantization, which is essentially scalar quantization across the entire index. So it's not just one vector, but it's horizontal and vertical. And product quantization saves a lot more space than scalar quantization. And it also is a lot less accurate when it comes to search. And so when you actually want to, so Milvus allows you to combine the scalar quantization, the product quantization with the IVF and the HNSW, which gets you, let's say you combine HNSW with scalar quantization, then you can get, the nice, like, oh, I don't have to have a lot of memory on disk, but I also get the nice accuracy that HNSW provides, right? So you can take these kinds of different methods, you can combine them, you can do different things with them to get better results. Okay, so I'm gonna jump into the demo. Before I jump into the demo, I think we should pause here for some questions. Let's see. Oh, okay. None of these questions need to be answered at the moment. Okay, cool. So let's look at the demo. So in a second, I'm gonna code up some. We're gonna look into a code demo, and this code demo is basically what we're gonna do is we're gonna download some embeddings models, and this is one of the pieces that has been asked about a lot. This is definitely an FAQ over the last year, which is how do I get my data into Milvus or Zillis? And so so we're going to walk through that example here with 3 different embedding models, but an even easier way is to use Zillis pipelines, which is something that we created pretty recently because we kept hearing so much about people wanting to get their data into a vector database. So once we download the 3 models, we're going to make up a data set. I will have a link so that you can just grab the data set that I'm using. And then we're going to embed that data with 2 different models, and we're going to ingest both those data sets into Milvus. This is just, bulk insert basically. And then we're going to query Milvus using that 3rd set of embeddings. So here, I'd love to get your idea on what you think will happen with these embeddings. Drop some comments in the chat and let me know.
While we wait for them to respond, we had a question just come in. It says the rank order of all 3 metrics are the same. Is that true? It seems not true to me.
The rank order of all 3 metrics are the same. I don't have like a mathematical proof for this off the top of my head, but we can at least easily see that the cosine and the inner product ones are the same because they are a simple transformation where you're being all of the cosines are basically divided by their magnitudes. L2, I don't have a transformation for this off the top of my head, but there is a way to transform that equation of xi minus yi squared and compare that to the cosine AB valuation. So the rank order for them should all be the same. Definitely all the same if you have normalized data. what are those different methods? I think was that about the metrics?
Yes, I believe so.
Okay, that makes sense. Okay. Has everybody had a chance to scan the demo and is able to see the notebook that we're going to be working with? Give this another minute or so. And if you have ideas for what might happen with comparing different embeddings and different embedding models, you should drop them in the chat. Okay, I think this is long enough to get this. So I'm gonna pull up my notebook, and we can drop the link to this notebook that the demo links to in the Zoom. So let me drop that in the Zoom. Okay, and then we will all right, cool. So I'm going to be doing some copy and pasting and some live coding, some actual live coding, and some copying and pasting. So the first thing we're going to do is we're going to copy and paste this. We're going to install PyMilvis, Milvis, and sentence transformers. These are the 3 libraries that we're going to need for this project. So I just did this earlier, so I'm really hoping that nothing breaks.
And if this is too small for the audience, just drop us a note in the chat and we can have Eugen zoom in the screen a little bit. So let us know if it looks good to you.
Oh, I'll zoom in a little bit. Here we go.
Great.
So this is what we're installing right now. And this is taking surprisingly long, actually. I'm not surprised. Oh, I also need to install pip, but we can do that later. We can install pip at a later date. Okay, so I'm also going to get a bunch of imports here. So here we're going to import sentence transformer from the sentence transformers library. This is how we're going to get the embeddings models. Then we're going to import the default server from Milvis. This is Milvis Lite. So this allows us to have a server that we can spin up directly from our notebook. And then I'm going to get PyMilvis. And from PyMilvis, I'm going to import connections, which allows us to connect, utility, which allows us to work with the schemas, and then field schema, collection schema, data type, and collection. So Milvis creates collections, and inside of collections, they have schemas. And inside of schemas, there are fields, basically. Fields are what are used to define a schema. And the fields are defined by data types. Okay, and then here I also have time. This is mainly just for measuring time. I don't know if we'll actually use it in this specific, I don't know, use case, I guess. All right, so let's see how this does. This is taking a really long time to import. I always get nervous whenever any of my Python notebook cells take longer than 10 seconds to run. It's like, what's going on?
It's the magic of live demoing.
It is the magic of live demoing, but it looks like it's working. It's definitely executing some commands here, at least. Wow, 30 seconds. This is taking quite a while to run. This is quite unusual. Oh, there we go. Okay, cool. Nice. Okay. So the next thing we're going to do is we're going to want to start the default server, and then we're going to want to connect to the default server. So let's do that. So default server dot start basically starts the server, and then connections dot connect. So here you'll see that this is localhost, and this is where the server starts by default. And then we also have a method that listens to what the port is that the server started on. And I think by default, this is 19530. Okay, here we go. Oh, nice. Okay. Right before I got nervous, 10 seconds. Okay, so the next part here, what we're going to do is we're going to download a bunch of, so I don't expect you to actually be able to like type all this quickly, but you can probably copy and paste it this quickly from the notebook. We're going to grab 3 different sentence transformers. And so you'll see that we're getting the multilingual mini LM L12. And you'll see that, these are all the same base. These are all the same base model. And so this is the base model from sentence transformers. And then the other two are fine-tuned. And these are fine-tuned on different data sets by different organizations. Okay, so what we're going to do here is we're going to rename these. So this is actually not mini LM v2 quantized, but probably a different one. But we'll leave the name here. So basically what I'm doing here is I'm giving two collection names, and I'm also defining this thing called dimension. And dimension is the size of your vector embeddings. It's the number of dimensions, the number of numbers essentially that gets that the machine learning, that the embedding model produces for your vector embedding. So all of these paraphrase multilingual mini LM L12 V2 models have a dimension of 384. And you can find this by either playing around with it inside the code and just getting the output and seeing how long that vector is, or you can read the model card. And then after we define these, we're just going to go in with the utility and just make sure that we have a clean slate and drop them if they are currently in the collection, not collection, database. So now we're going to define our data. So I copied and pasted a bunch of this data. This is inspired by Speak Now. I took Taylor's version, although really, I think I made this initially when she came out with her version of Speak Now. Actually, no, that doesn't sound right. No, I'm not entirely sure. Anyway, I pulled some lyrics from these 4 songs, and you can just see that, they're all basically sentences, and there's like 50 of them. So this is how we're going to do some embedding comparisons, and we'll just see how long this is. I believe there's 51. There's 51 of them. And so with 51 sentences, it's really, this is very much a toy example. There's not a lot of results that you can get back. There's only 50 of them. So just keep that in mind. Okay, so now let's define some important parts of our schema. So what we're going to do here is we're going to define the schema for our collections, right? So we have these 2 collections that we have 2 collection names for them, and we're going to give them the same schema. And so in our schema, what we're doing is we're going to define the fields. If you remember earlier in the presentation, I was talking about how there's only 2 fields that really need to be defined, and those are the ID and the embedding, and the rest of the fields are metadata fields. So here, we define the ID and the embedding. And unlike the example, I'm going to use an auto-incrementing integer as my ID. And then here, I have to tell the database that the dimension of the vector is 384. And then I just say enable dynamic field equals true. And this allows me to insert basically whatever metadata I want without having to predefine it in the field schema or in the collection schema. And actually, we just wrote a blog about this. And so we should put a link to that in the chat. But there is a blog about that tells you a little bit more about how dynamic schema works and what it is. The next part here is we're going to get the actual embeddings. And so the way we do that is we're going to go and you see we have these models, right? Remember, we got these models up here. Where are the models? The models up here. And then what we're going to do is we're going to call this function called encode. And essentially what we're going to do is we're going to encode, we're going to create a dictionary here that's going to map all of the sentences to their vector embeddings. And so this should take just a little while to, oh, wow, that was really fast. Oh, that's nice. Okay. And so what this will do is this will give us our first 2 sets of embeddings, right? So we have these 2 models and we're getting all of the embeddings from these 2 models and we have them mapped. And so now what we want to do is we want to create how we're going to create the index on these 2 sets of vectors, right? So remember we talked about the vector, the indexes, and the distances. And so here, when we create the index, we're going to have to keep that in mind. So IVF, right? This was the first index that we talked about, the most intuitive one, the one that's basically just creating a bunch of clusters. And then flat. Flat means not quantized, right? So the other examples that I gave were SQ and PQ, scalar quantization and product quantization. Those are good for reducing memory consumption. But since we have a very small number of vectors, then it doesn't matter. And here we're using L2 as our metric type. And then for our parameters, nList is for IVF, what this describes is how many clusters do we want. And since we only have 50 data points, 4 clusters is probably a fine number of clusters. Okay, so now what we'll want to do is we want to create these indexes on these fields, and then we want to load the collections in memory so they're loaded up in memory so we can work with them. Okay, so now that we've done that, what we're going to want to do is we're going to want to insert a bunch of data. So remember up here, we created this dictionary, these 2 dictionaries of sentences. And remember up here, we created sentences, which is our list of sentences. So what we're going to do is we're going to go and we're going to create an insertion function. So this is a list of dictionaries, mainly because it's meant to be used as batch insert, and I'm using it here as single insert. But you can use this to insert hundreds of data points at once. So basically what I'm doing here, I could probably batch insert the entirety of all 50 of these at once. So basically what we're doing here is we're saying like, here's the sentence, here's the embeddings. And notice that I don't identify or I don't define ID in the insert. And that's because ID is going to auto increment. But notice that I also define this new field called sentence here. And the way I'm able to do this without having defined that before was the dynamic schema thing. Okay, so basically what we're doing is we're creating a bunch of things to insert, and then we insert them, and we call flush on the collection. And what flush does is, in Milvus is a distributed system that holds a bunch of memory in these nodes. And so what flush does is initially your memories and nodes flushes that memory into permanent storage and creates the actual index on that data. Okay, so now we're going to find a way to search these embeddings. So search embeds, I'm going to once again create a dictionary. And what I'm going to do is I'm going to create, I'm going to take some sentences from the sentences. I'm going to take the 5th and the 6th sentence here. And I'm going to encode them using the model that we didn't use before. And then I'm going to map them, and I'm going to have it appended into a list so that when we search Milvus, we can just give it this list. Okay, here we go. This is a little bit of a complicated section, so I'm going to pause here and explain this. As I was saying earlier, time is was basically just for me to see the experiments here. But what we're going to do is we're going to give it the data, right? So data is the data that we search with, and we're going to pass it this list of vector embeddings. And then we're going to tell it the approximate nearest neighbor search field, ANNS, approximate nearest neighbor search field, is embeddings, and that's the embeddings field, right? That's the field that we compare across. And then in order to search it, we have to use the same metric type, LM, or not LM, L2. And then in parameters, we have to tell it how many clusters to look at. We only have 4 clusters. Let's just look at 2 of them. And then let's say we only want the top 3 results. And the output field, which is the output, the fields, the metadata field, essentially, that we want to pull from the database is sentence. And so we'll do that here for this collection, and then we'll do the exact same thing for this other collection, right? We're going to see how this is a one-to-one repeat, search data, embeddings, L2, probe 2 clusters, limit of 3, output the field, output the sentence. So let's see. So the time here, you can see the search time for Milvus is insanely fast. And then we can see what the actual values are. So this is the first one, and we'll see what the query sentence is and then what the nearest neighbor is. So I probably should have separated this into these 3 and then these 3. But you'll see that the query sentence is like, I don't know what song this is. Oh, I know, this is Speak Now. So this is the query sentence, and this is the result sentence, and you'll see that these are not the same. So that tells you that these 2 embeddings models have very different embedding spaces, because none of these 3 sentences here are the same sentence as the query sentence, which is something that you would expect to see if you were going to use the same embeddings model. And once again, you see that these three, also none of these nearest neighbors are the query sentence as well. So that tells you that these two embeddings models have quite different embedding spaces, despite the fact that they're the same base model. Okay, so now let's look at the other one. And this will be the last thing that we're going to take a look at today. Where's my, there we go. Okay, so the other one looks almost similar, almost the exact same, right? So you'll see that this one is actually the same result. This one is different. And oh, hey, here we go. We actually get the same sentence back here on the third one. So this is interesting. This tells you that, these models were able to map these two sentences into similar spaces, but not the exact same. And this also tells you that, here there's actually a couple crossovers between these first two, right? They're right here. These are the same too. And then here on this one, you can see that there's once again no repeat of the same sentence. So this really demonstrates how important your vector embedding model is, and how it's very important to the results that you'll get from working with your vector database. Okay, cool. So that's pretty much it for this demo. I think we can take questions now. Where did you specify the embeddings models as different? Okay, so I will go over that again. So see here, we get the sentence transformers. Here, sentence transformers. And then later on, we get the sentence transformer. So what this does is this loads this specific sentence transformer. And you'll see that I loaded 3 sentence transformers here. And then with these 3 sentence transformers, you'll see that what I do with the data is I encode the data with each of these transformers to embed, this is the embed basically, by the way, and to store into Milvus. And then when I do the search, you'll see that we use the last one to do the last embedding. So that's where we specify the different embeddings models. Are there any PyMilvus embeddings utilities geared towards time series data as opposed to image text, or do the same functions apply? I think the first thing to answer here is that PyMilvus does not have embeddings utilities. The embeddings here was done completely with Hugging Face. Zillus Cloud does have a way to allow you to automatically just do drag and drop your data. You don't have to worry about the embeddings. I think it only works on text data right now. But I'm sure that there are plans to have images, audio, time series, whatever other kinds of data in there in the pipeline. But in the pipeline, yeah. And the tool is also called Pipelines, and it's available for free to anyone who is using a Zillus Cloud free tier or a serverless cluster. So that is one way that you can get your embeddings in, as opposed to when it comes to time series versus text versus image data, what matters is the model itself and what it was trained on. So if you have a model, or if you know of any models that were trained on time series data specifically, then that would be the type of model that you would need, the type of embedding model that you would need to get time series data.
Any other questions? Feel free to drop them into the Q&A tool at the bottom of the screen. Eugen, you've talked to a lot of people, you've helped a lot of people get started with Milvus. Where do you feel like most people struggle, and what tips do you have for them?
So I think we've, I'm going to stop sharing here. So I think we've covered this a little bit. Most people have trouble getting their data into Milvus. This is something that I get a lot, and something that I've been thinking about, like, how do we best address this kind of a challenge? And one of the things that I think makes it difficult to deal with this or to make it easier for people to get started with is just that there's a lot of misinformation, and it makes like the way that things are framed almost makes it seem like there is image vectors or there are text vectors. But that's just not true, right? So like the vectors themselves are really numbers, right? And this is something that this is something I tried to, get across in the presentation a few times, which is like, take the numbers, the output from the second to last layer, and then the image of the embeddings, which are the numbers, and then when we did the input, I didn't show the embeddings when we did the demo, but image and text are just two types of unstructured data, and when you put them into vectors, they're all become just series of numbers. And I think the reason why there's confusion around this is because image vectors and text vectors are typically different lengths. And I just use the terms image vectors and text vectors, despite the fact that I was just talking about how these things don't exist. But vectors created from image data, models trained on image data, typically have a different length than of their second to last layer than models trained on text data. So I think that's one of the biggest challenges that I see. The other challenge that I think I get, the other question I get a lot is people talking about LLMs versus embeddings models, or if there's any difference, or even when it comes to RAG, people ask, what does the LLM do? Can I do this with just a vector database? And then, I also get the other option, which is the reverse option, which is, oh, I have an LLM. Why do I need a vector database? And so I'll just answer both of those. So with a vector database, the reason why you would drop an LLM on top to do RAG is, for example, if I ask the question, oh, I didn't have a good question off the top of my head. What's the most similar fruit to an apple? And in my vector database, I have a bunch of text stored there. What it'll do is it'll pull the most semantically similar questions or semantically similar text back, which will probably be things like, what's the most similar fruit to an orange? What's the most similar vegetable to a tomato? Or things like that, or tomatoes or fruits. But it wouldn't be able to say like, oh, like what I actually want is I want to find the thing that's most similar to the word apple, which is what the LLM would do, is would break down that query and say, here's what you should actually search for that's semantically similar. And then the other way around is, why would you put a vector database under an LLM for RAG is the LLM doesn't have access to your data. It doesn't know like what you were working with, and it doesn't have the context of what you're working with. And so with a vector database, what you do is you take your data, you vectorize it, you insert it into the vector database, and then during RAG, you pull your data from retrieval augmented generation, is literally like it's generation that's augmented by data retrieved from the vector database. And then you put that in as context into your LLM prompt, and then you'll get some sort of more human readable response.
Thank you. Rishi's got some questions. They're running into an issue with the Google Collab. So there's some details in the chat for you to take a quick look at.
Yeah, that's just a dependency issue. Probably want to pip install PyArrow there. Maybe see what libraries you have installed there, Rishi.
And then we have a question: is Milvus LLM agnostic, or is it or is it used to have better performance with some specific type of LLMs?
Yeah, Milvus is totally LLM agnostic. LLMs have, I mean, like LLMs and vector databases are entirely decoupled. So yeah, there's no, it doesn't have better performance than any specific LLM. You can bring whatever.
Great question, though.
Yeah. Same with embeddings models. It's also entirely embeddings model agnostic. You can use whatever embeddings models you want, and you will get the same results. Not the same results, but like, the same quality of results.
So Eugen, you've done a bunch of projects. Some of them are image-based, some of them are text-based, a lot of them are Taylor Swift-based.
Taylor Swift.
When you go to start a new project, how do you think about choosing your embedding model? Like, do you sort of kind of continuously use sort of the same ones? Like, what is your sort of research approach? Because I know there's so many options out there now, especially in the open source model world. So how do you sort of think about choosing, and what are you looking for?
Yeah, that is a great question. And so I don't do too much experimentation with the embeddings models anymore. And the main reason is because I spent a few months basically just playing around with embeddings models last year. And that's actually how the demo that we just walked through came about, was because I was like, oh, it'd be cool. We should compare some embeddings models and see how different they are and how similar they are and whatever. And what I actually look for when I do my testing, when I was, I guess, doing more experimentation, a lot of what I was looking for was like, you know, does this make sense? And like, so for example, when I was working with images, that paintings one, the things I thought about with does this make sense is, if I'm going to give a similar painting, I better be getting the painting back in the top three that I expect to get back. It's like it looks similar. So I think the one that I did the test on was the Sea of Galilee, and I was like, oh, there better be a boat and there better be some water. And then with text, it's more like you know does this make does this make sense? Like, this is text back. Like, it's a lot of it is just human. Like, does this make sense? Now, there are actually eval methods that people come up with where they use LLMs to evaluate the results from the LLMs and the results from the embeddings models. But the challenge with that is that eval method evals the entire RAG app, the entire stack, and not just your embeddings models. And it's actually, I think the thing with embeddings models is it's actually very hard to judge if your embeddings models is the right embeddings models. And the real answer to what you should be doing with embedding models, especially in enterprise production, is create your own embeddings models or fine tune an open source one, and make sure that you put in the data types that you want to relate into it that relate to each other, so you get one that operates in your latent space.
Awesome. We have another question. Is there a way to visualize the vector DB to create a knowledge map?
Yes. So you can create if you literally just look at the HNSW index, that is basically a knowledge map. But another way you could do it is you could actually take all the vectors, download them, and then you map them into a three-dimensional space, and look at that on what is the thing that lets you do that? I think matplotlib lets you have three-dimensional space. I think you can do that in matplotlib. And so you can just download them, you map them, and then plot them into three-dimensional space and see what the clusters look like. And that's actually the basis for a lot of eval methods, and it's similar to what a lot of open source eval libraries do.
Doesn't Galileo have some visualization tools as well?
Yes, so Galileo and Arise Phoenix, and TrueEra, TrueLens, and YLabs, YLogs all do very similar things that they'll basically allow you to do that visualization.
We have a great question. What is Milvus built on top of? Is it MongoDB?
Aha, yes. Actually, I heard that Atlas was in talks to use Milvus for their vector search, or that MongoDB was in talks to use Milvus for their vector search. But Milvus is actually built from the ground up for it's built specifically for vectors, right? So MongoDB is built as a NoSQL database, which is built for key-to-key search, and they have to implement a vector search on top of that is able to kind of run that without having to do I'm going to search through all my vector or all my entries. So we are built natively to work with vectors, and we're built on top of Kafka and MinIO, Kafka or Pulsar. Milvus is modeled as a pub subsystem, so you publish data and it's just like a streaming data, and it just goes out, and it's essentially if you think you have a Medium account, you're just publishing things on your Medium account, and then there's the subscriber, which is people who are maybe they're adding your Medium account, maybe they're adding your Medium publications to their list or something like that. So yeah, that's kind of that's how you can think of the way that Milvus is built. We will probably do a more we'll probably spend some more time doing a deep dive into Milvus at a later section. But Milvus is not built on top of any existing database. It is built from the ground up.
And I'll just add to that, the reason that we, that the founders and the original creators took that approach was really to be able to build it for scale. So I think there's a lot of new emerging sort of vector search tools that probably work fine for very small data sets, which was never really the intention of Milvus. Milvus is really meant for billion, 10 billion scale. So, if you have 100,000 vectors, a lot of options work. But if you're talking 1 billion, 5 billion, 10 billion, scale and having it purpose built for vector data is really important. So that's kind of where we specialize. Let's see, what
Yes,
does a vector database expert mean, same as SQL Server expert, or is it
no,
completely different?
completely different. Uh, um, these have nearly nothing to do with each other. SQL is the SQL databases aren't even built with the same intention that vector databases are built with, right? So SQL databases are built with the intention of letting you store entities with known attributes that you want to be able to create relationships with at query time. Vector databases are meant for you to store the semantic meaning of entities as a list of numbers and allow you to compare these vectors at query time. So the intention behind these two databases is entirely different. And maintaining the databases is probably also a little bit different, although you could argue that containerization and scaling and auto scaling and all these things are very similar when it comes to doing DevOps on the back end.
You have some benchmark in terms of performance comparisons among other vector DBs. You want to tell them about Vector DB Bench?
Yes, I do. There's Vector DB Bench, which I actually was in the list of open source projects that Zillis maintains in the slide that I did not mention. Thank you, Emily. Yes, so we have a open source benchmarking tool that you can use that you can compare all the vector databases and you can bring your own data. So it's open source and you should check it out.
Well, I think that's just about all we have time for. It looks like we've gotten through all of today's questions. Thank you everyone for joining us today. We hope to see you on a future webinar. You can check out zillows.com/event for all of our upcoming sessions. We've got one on text embedding a little bit later in the month. Eugen, thank you again for doing such a great session, and we hope to see you all next time.
Thanks. Thanks for coming, everyone.